Okay, good morning. Today we are going to complete our lecture or example on transmission shaft design. Then after that, we are going to go into design analysis of beams under combined loads. Okay. So where we finish off on Wednesday is we have determined the moment about the y-axis. Okay, so we determine the moment at point A, point C, point D, point E, and point B. Okay, so the next thing that we're going to do, I'm going to copy this diagram. This diagram I need it for the next one. Is we're going to take moment about the y-axis. Okay. So moment about the y-axis is moment going in this direction. Okay, sorry, z-axis, not y. We have done y already, so it's moment about z. So now we are going to view the shaft, or we're going to view in the xy plane. And this is our rotation in the z. Okay, so we're going to view it in that way. So I'm going to sketch the shaft. So this is our point A, our point B, our point C, D, our point E. Okay, then I'll sketch our centroid. Okay. So at A, we have a force going at 932. At C, we have 6632. At D, we have 2487. At E, it's coming down at 3730. And then at B, we have a force going at 2797.5. So like what we've done before, ignore the dots and crosses. Okay, so we are going to draw out the moment about y. Okay, so we are going to create a table. Sorry, moment about z. I'm still not awake. Okay, so this is our existence. Okay, so this is our point A, our point C, D, E, and our point B. And we know at point A and point B moments are equal to 0. Okay, so that's where point A and point B. So we are going to calculate moment at point C. So I'm going to take anything that goes anti-clockwise as positive. So is equal to, so I can take the 932, right? So 932. So 932 multiplied by 0.2. So the moment is equal to 932. It's equal to 186.4. Okay. So for this case, we are doing the analysis from right to left. I'll say why I do this, okay? So what I did is I take moment at point C, okay, where I take the moment point C, right? I do the analysis from, sorry, this is left to right. Left to right. Right, I go this way, left to right. If we were to do it right to left, the answer will also be the same. Okay, so this is also the same. Again, I take summation of moment Z at point C. So this is equal to 2797.5, 246 multiplied by 0.6 minus by 3730 multiplied by 0.4. Okay, so this will be equal to 2797.5 times by 0.6, which is 1678.5 minus 3730 times 0.4 is 1492. Okay, so this will be 1678.5 minus 1492 is 186.5 Newton meter. So this is from right to left. Okay, so you can do it either way. Your answer will be the what? Will be the same, similar. Okay, down here is by 0.4. This is by 0.5. Okay, it's just 0.1 of a Newton meter difference. Okay. Right. So next we are going to find the moment at D. Again, anti-clockwise summation about moment at Z at point D. So it's equal to 932 times by 0.4. So 932 is 372.8 Newton meter. In this case, I'm dealing from left to right. Okay. Why I'm doing that? Because if I do left to right, I only have 932 to consider. Okay, I don't need to do the 3, so you got more steps. But I've shown you that the answer is the what? It's the same. Okay. And lastly, as I mentioned, our anti-clockwise is positive Z at point E, right? So I'm going to take from right to left now. Okay, so it's 2797.5 multiplied by 0.2. Okay. So 2797.5 times 0.2, 559.5 Newton meter. So this is right to left. If I were to do the same from left to right, okay, again, I only need to take one force because there's only one force component. And we multiply by 2 force 0.6. So 932 times 0.6 is equal to 559.2. It's about the same. So this is left to right. Okay. So now we know that we have 186.5 at point C. Okay. So this is 186.5. And then at point D is 372.8. 372.8. And at point E, you have 559.2. So this is just a sketch, okay? So you have 559.2. Okay, so this is moment of Z. So from here, we can sketch the magnitude at point C, point D, point E, and then coming down point B. Okay. So this is moment about Z. Let's compare. Okay, I'll come back to here. Let us compare to the moment in Y. So we did this on Wednesday, right? And let me zoom out. Okay. So if you look at moment about Y, so the bottom graph is moment about Y, and the above one is moment about Z. Okay, so moment about Z, the maximum bending moment generated is at point where? E. Whereas moment about Y, the maximum moment generated is at point C, as you can see there. Yes? Okay. So what we are trying to achieve down here is we are trying to satisfy or find the equation J over C is equal to square root of Tx squared plus by My squared plus by Mz squared, and then divide by shear stress allowable. Okay. So we are trying to find the diameter of shaft AB. And we are almost there. Okay, this lecture has gone on for what? This is going to be our second hour of doing it. Okay, so we have found our My, and then likewise we have found our what? Mz. Okay, we have found our My. Next is the torque at X. Okay, so the torque at X we have more or less calculated, more or less calculate the value already. Okay, so what is it? Okay, so again, okay, I'll let you guys copy this first. Okay, so we are going to analyze the torque in the X direction. Okay, so we have compute this, or we have calculated this before. What do I mean by that? Okay, so this is our X, again, Y, and Z, point A, point B, point C, point D, and point E. Okay. So if we were last week's notes, if I can refer it to, I can refer it quickly. Okay. So we have done this calculation. Okay, we have done this calculation. We have calculated the torque. This is on Wednesday. No, we calculated the torque point C. We have calculated the torque at point D, and we have calculated the torque at point E. Wrong, circle the wrong thing. Torque at E, right? So T and C, if we go back to our original or our diagram, C and D are output. Yes. Yes. No, because everything's squared, right? Everything. Lucas asked, "Do we don't care about the sign?" The answer is no, because they're all squared down here. Okay. Now this method is only good for sizing. Okay. If you are designing a shaft that is made of carbon fiber, you cannot use this. You need to know whether is it positive or negative or the direction of the shear. For this case, it's not important, right? You've done 3CO3 with me, right? Yeah, that's where it's important. You need to know the principal stress. This, we are just finding the diameter. We are not bothered about the principal stress. Okay. Right. So when we come back to here, okay, so I was talking about the torque now, okay? So we know that gear C and gear D are generating an output to the system, right? There's a load or output load. Whereas gear E is the input load because it's driven by the what? Motor, okay? So watch this, okay? So gear C is 397.887. So we go back here. Okay, so it's going this direction. The torque is 39. My memory is so bad. 397.887. Right? And at D, the torque the top output, okay, is generating at 198.944. Wait, 9944. Okay, so at point C is output, at point D is output, right? The torque is going to output. At point E, where the torque is what? Input. So the direction will be what? Reverse, right? So it's 397.887 plus 198.944 is equal to 596.831. Okay, so if you go back to this graph, the 596.831, or this information over here. Okay. So next, we are going to sketch the torque distribution. Okay, the torque distribution. So and this